Okay, let me introduce our third talk. The topic is Downscaling Spark on Google Cloud, and our speakers are Ben Sidom and Karthik Laniappan.
So I'm Ben. This is my colleague Karthik. We're software engineers on Cloud Dataproc, which is a Google product. Before we get started, I just want to get a read of the room. So how many people? Obviously, everybody's heard of Spark. How many people have used Spark recently? Okay, so a decent number. And how many people are familiar with Cloud Dataproc or Amazon EMR? One of those two. Okay, so I'll let Karthik actually introduce what that is. We'll try to keep the talk short because I know you guys are all tired after eating your pizza and want to go home now. We'll start by introducing Dataproc and the notion of elastic Spark clusters, and then we'll discuss what we call the shuffle and or downscaling problem, which is not specific to Spark, but execution engines in general. Solutions that we've come up with for the downscaling problem, and then finally future work.
Alrighty, so Google Cloud Dataproc is the managed open data analytics platform for Google Cloud. Ben and I are primarily familiar with Spark, but we also provide Hadoop like MapReduce, Hive, Flink. If you use Jupyter Notebooks, Presto, and Drill, so there's plenty of stuff. But today we'll primarily be talking about Spark. So we see Dataproc as kind of the connection to the rest of Google Cloud Platform as well, and also kind of supplementary to it. So you could, for example, store your data in BigQuery or Google Cloud Storage, which means that you can query the data using BigQuery, but also keep using tools that you're familiar with, like Spark. And so to kind of hammer this point home, what's really special about this, and kind of what's special about cloud in general, is you can separate compute and storage. Have you guys heard of this concept before? Yeah. So I mean, since folks have heard of Dataproc and EMR, and that kind of makes sense. But for those who aren't familiar, the idea is you can scale your storage and scale your compute separately. And so this gets more and more interesting when we're talking about auto-scaling, because now storage is just kind of this solved problem. You put your data in Google Cloud Storage, it's kind of no hops. It's now it's just we're worried about how do we scale the compute side of it. So there are two kind of models that we talk about and one on the left is something that's kind of special to cloud, I think. So the one on the right is kind of the model on-prem users might be more familiar with, where you have a monolithic long-running cluster that users submit jobs to. Because this is cloud, that cluster can scale up and down. But the model on the left, I think, is really interesting. It's this concept of ephemeral clusters. So what this means is you can have one job or one workflow run in its own dedicated cluster. And so you get isolation, so you're not competing with other users, both from a security perspective, you have your own permissions there, and also you're not competing for the same resources. I can just say, my job gets 5 VMs, and I'm getting those 5 VMs. No one else can preempt me. And that is really, I think, unique to cloud. Sorry, I stepped on the cable there. Nice, there. So I haven't talked about where this stuff runs. So Dataproc, by default, we run primarily on Yarn. And that's kind of the standard in the industry. We also have an alpha for running Spark and Kubernetes, with like our managed service.
All right. So because we run on cloud, there are some specific flexibility features that you get, including the obvious ability to scale out or scale down. So first of all, we offer different types of machines. So there are different shapes of general purpose machines. If those don't suit your needs by default, then you can tune the number of CPUs or the amount of memory per machine independently, and those scale the prices scale with the resources that you use, and you can come up with virtually any shape that you might need for a job. So if you have a compute-intensive job, you would use a machine that has less dedicated memory, or vice versa. And And this is something that's a little bit more special. So there's something called preemptable instance, or preemptable VM, or PVM as we call them often. And those are basically identical versions of regular VMs, except they might be preempted at any point in time. And the most common reason to use this is for the cost saving. So because we're able to sell the excess unused capacity on GCE, we'll sell to you for usually about 20% of the price of a regular VM. But it might be preempted at any point in time. And when the preemption event happens, you might not get the machine back for an arbitrary amount of time. So this is something that's perfectly, or at least in theory, perfectly suited for a distributed workflow that you want to scale up and down with excess capacity. You're willing to throw some money at it, but you don't want to put too much money into it because it's just going to make your job run faster. It's not necessarily going to change the correctness. On the other hand, it's not great for, or using these kinds of VMs is not great for any sort of mission critical workload or latency sensitive workload where you wouldn't be able to tolerate a machine outage that just comes out of the blue. And then finally, something that's important to realize is that we have different disk types on cloud, and by default, at least on GCE, we use something called PD, or persistent disk. And persistent disk is, as it sounds like, is a type of disk that's replicated for you automatically. But as a result of that, it doesn't actually live on the machine. It's not rack local. It doesn't act as a standard hard disk. Instead, it's all data access goes over the network, which means you also incur network-based throttling. So I have a chart here that shows how the throughput that you are allotted on GCE scales with the disk size. Don't worry about the actual numbers themselves. You can find those on public documentation. But the point is that the characteristics aren't necessarily what you'd expect. And then we also have something called local SSD, which is literally rack local. That acts more like something you might be used to if you've been running on-prem. And the idea is that it's meant to be used for high throughput, high IOPS, local scratch work, basically. All right, so then shuffle itself.
All right, so preemptable VMs sound great, and autoscaling even sounds like a great concept because we're just scaling compute queues. But it gets more interesting when we're talking about shuffle. That's really the core of this talk. So just kind of for people who aren't super familiar, shuffle is really the core of any of these like sort of MapReduce type workloads. So the map phase of a job categorizes input partitions. So mapper one up here categorized green squares, yellow circles, and blue triangles. And then reducers take data that's relevant to them from each of the mappers. So reducer one, the green square reducer, went to each of the nodes that mapper ran on and asked for the green squares. And then its job is to aggregate that data. So that was kind of the core concept of MapReduce, and then Spark generalizes that into a DAG. So between each of the stages is a shuffle boundary where a shuffle like this has to happen, and it always happens on disk. So and actually, to be clear, when mappers write their shuffle data, they write their shuffle data to their own local disks. So there's two problems. So if when Ben was talking about preemptable VMs, where a VM can get preempted at any time, and actually GCE guarantees it will be preempted within 24 hours. So you're kind of taking a bet that that VM is going to be up for the runtime of your job, because if it gets preempted, you've lost that shuffle data. So like for example, mappers all succeeded, the reducers are running, chugging along, grabbing data from the mappers, and suddenly one VM gets removed or preempted, and suddenly all of your reducers fail, because every single reducer has to read data from every single mapper, and that's kind of the core of this problem. So even one preemption can set back the job progress pretty significantly. And I'll just throw in here, so we just talked about preemption, and I also just want to talk about autoscaling as well. The reason that this also becomes a problem without preemptable VMs is that autoscaling, both in here we're talking about data prop autoscaling on Yarn, but Kubernetes has the kind of equivalent concept of a horizontal pod autoscaler. So what these autoscalers are doing is they're looking at containers and seeing whether a node has containers or not. So like let's say that all your mappers ran, and now there's a few reducers left. It looks like most of the cluster is actually idle. So you'd think, for the autoscaler is thinking, well, let me just remove all those nodes that are just doing nothing and just wasting resources. But the problem is those nodes actually need to stay around to serve their shuffle data. So you actually can't remove them yet. So the general solution that we've had for a while is Yarn has a concept of graceful decommissioning, where you can drain a node. You can just keep the node around while the application is still running, just to give it a chance to serve its shuffle data. But if you have downstream stages that take a while, like if you have a job that runs for hours, then you have to keep that node around for hours. Otherwise, you have that same problem of now you're going to cause all the later stages to fail. So now the rest of this talk is kind of on better solutions to this problem that actually allow for more aggressive, both auto-scaling and also aggressive use of preemptable VMs that are cheaper.
All right, so the one obvious approach you might consider is, well, why not write the shuffle data to HDFS, that is the Hadoop distributed file system that ships with your cluster, rather than to local disk. And so for those of you who aren't familiar with the structure of it, the way it works is you have a name node, and you have a bunch of data nodes. And the name node is basically responsible for serving metadata and locking and performing file system-based operations. And the data nodes themselves actually serve the block data. Furthermore, on data proc specifically, we have a notion of primary workers and secondary workers. And in this case, primary workers and only primary workers serve as data nodes themselves. So they actually host block data. And if you scale up, your primary worker group, you get more HDFS capacity. If you scale down, you get less capacity, and you might need that might induce a data migration where blocks are offloaded from the nodes that are going away onto the other nodes. And then you have secondary workers, and if you request PVMs on data proc, those will go into the secondary worker group by default. They cannot go, in other words, primary workers cannot be preemptable VMs because they might go away at any time, and you don't want to lose HDFS data. We do have an undocumented feature where secondary workers don't necessarily have to be PVMs. They can be regular workers that simply don't participate in HDFS. And so the way HDFS shuffle works is pretty much exactly what you'd expect. The map executors themselves write to HDFS, or actually in general HCFS, which stands for Hadoop Compatible File System. So a Hadoop Compatible File System is just something that implements the HDFS Java API, not the HDFS wire protocol. And what it means is that you can plug in different endpoints, such as a block storage like Google Cloud Storage. And if you do that, then the data doesn't even live on the cluster itself. It lives elsewhere in the managed cloud storage service rather than on your machines. Anyway, so the map executors write to whatever HDFS endpoint you've configured, and then the reduce executors read from those directly. Something that I want to call out in this case, though, is that the partitions, as they show up on HDFS itself, are laid out in the same way that the mappers see them. Actually, you can see that the first partition is a square, circle, triangle, and as are the rest of them. And the reduce executors are still responsible for effectively merge sorting that data as they go through. So in the case of preemption, we don't lose progress, despite the fact that reducers are running actively, because the data doesn't live on the map executor machines, it lives in HDFS. This is just some rough numbers. It's a little bit noisy, but the important thing to notice is that the runtime scales super linearly when you use the HDFS-based shuffle service with the number of partitions that you have. And so it degrades actually both in terms of number of partitions that you have and in terms of data size. And after doing a lot of debugging, we determined that part of this was due to name node bottlenecking. So every time you do a file system operation on HDFS, you do a round trip to the name node. That often results in excessive synchronization. You don't need all this stuff when you're writing and reading shuffle data necessarily. And then on top of that, HDFS is not optimized for for reading and writing small blocks at a time. And so, in general, every single reducer is going to read from every single map output file, but it's only going to read a really small segment, maybe a 20 kilobyte segment. And so HDFS is very much not optimized for this, and it's not, it doesn't scale well.
So take two. So yeah, so to be clear, the reason that that's particularly slow is that, so shuffle is an M times R algorithm. So I have 10,000 mappers and 10,000 reducers. I have like on the order of M times R, so 10,000 times 10,000 IOPS, essentially, because like that's how many chunks need to be read in total. Because each mapper writes one chunk per reducer. So with HDFS, the bottleneck there is the naming, because every reducer needs to make 10,000 calls, one for each mapper, to get each chunk of that mapper's file. So this kind of take two here, the idea is let's cut out the name node as a middleman and kind of go back to the way that Spark Shuffle normally works, except instead of putting the Spark Shuffle service on all the nodes as it is normally, so instead of just writing to your local disk, you just put the Spark Shuffle service essentially on the primary workers, on the pool that's fixed, and then now you let the auto-scaled pool write to those primary workers and let them serve the shuffle data normally. So what this also means is that we get to reuse a lot of code in Spark. So actually my prototype of this was maybe like 200 lines of code, because it's a very small change to just make the Spark Shuffle service accept blocks in addition to serving them, and a very small change to the map side to write to that shuffle service. And then benefit number two is that all of the tuning advice in Spark in general still applies. So the reduce phase works as normal. You still go to each of the nodes that the mappers wrote to, and you get your relevant chunks of the data. So my price performance discussion here, I was benchmarking a 10 terabyte shuffle with 58 core machines. The baseline has 50 primary workers, so nodes that cannot be preempted. And then with my prototype, I had just 5 primary workers and then 45 preemptible workers, which makes the job a lot cheaper. So I saw a 10% performance degradation, but the job was 50% cheaper. So half the price. This isn't necessarily the best long-term solution because it does degrade performance and still requires a fair amount of tuning to get this to work. But the intuition behind this is that a lot of data proc clusters use the default persistent disk, which is backed by hard disks. And so if you use local SSDs, then the disk throughput and IOPS of your cluster goes way up. And so you can just fill the primary workers with a lot of disks, and now you can point, in my case I was using a 9-to-1 ratio of preemptive workers to primary workers, and I was still able to handle that shuffle. So I still had the throughput and IOPS just from the 5 workers that were primary workers.
All right, so the experiments look good. This works pretty well. It's something that Spark knows about, and so there's actually stuff happening in the Spark community right now. The primary one being Spark 25299. So this was open as a SPIP, and there's public documentation that you can read along with if you're interested in this effort. But basically, it is taking that the first idea, sort of the HDFS shuffle backend, and generalizing it. So allowing you to swap out HDFS or the local file system with an arbitrary storage system of any type. It doesn't necessarily need to live on the cluster. It doesn't need to live. It doesn't have to be an external managed cloud service. It could still be local disk. But the key is that it still uses the same sort-based shuffle algorithm. So that means that both the mappers and the reducers during aggregation stages need to potentially spill to local disk when they're actually collating the data and splitting it into output provisions. There's another effort going on in parallel with that to actually generalize the shuffle interface for Spark to make it work beyond that. And so it involves a few things, but the basic idea of it is to allow a completely remote service-based shuffle to work. And to get that to work, you need to add a few things to the map output tracker, such as adding payloads that shuffle managers can stuff into partition metadata, allowing the output data to be dynamically updated. So, for example, if you have some sort of caching layer that you're writing data to, rather than a fully replicated HDFS service, you might be able to write shuffle data out as you're executing your map tasks, but you might want to mark those as actually no longer available at some future point and allow the Spark scheduler to rerun those. And then there's stuff like deterministic serialization for aggregation. I could talk about that afterward. It's actually kind of getting into the weeds. But basically adding these things allows you to turn Shuffle into a fully remote service rather than just a small part of the actual Spark pipeline itself and coupled with the system. And so it enables Costco Shuffle, which is that's a talk that Facebook gave recently at one of the Spark summits about basically taking the output partitions and merging them, or a fully managed cloud shuffle service. And so this is what it would look like in this case. So if you recall, actually let me just go back to that page. If you recall the HDFS shuffle, if you look at the storage, again, the map executor representation is exactly the same as the representation on HDFS. And so the reducers, when it comes time to read, have to do that collation and merge sorting for partition. In the case of a completely remote unified shuffle service or integrated shuffle service, the mappers still write their segments, and you know they don't have to merge, sort, or do anything on their sides. They write to the shuffle service itself, and then the shuffle service itself runs its own sorting algorithm. And that algorithm might merge just by partition level itself, which is effectively all it can do given the current Spark APIs, or it might actually group by key, like it might actually group at the object level. And if it were to do that even further, that means that you can think of these these green squares as not just specific elements within or not just arbitrary elements within a partition, but actually grouped elements, which means that the readers, when they come through, know that they have all of those, all values, say, of the key foo grouped together at one time, and you can immediately operate on that. And so this gives you a sort of consistent pre-computed view of the data set from either the mapper or the reducer side, reducing the runtime of the actual executors themselves, and also allowing them to scale because the remote shuffle service lives separately from it. So that's what we have, and I'll just open up to a Q&A if you guys have any questions.
All right, well, thanks for having us.
Yeah, thank you.